Okay, lesson 1, graphing functions with transformations. So by the end of today's lesson, we'll be able to identify base functions and then graph functions using transformations. So a table of values is a useful method for graphing functions, especially if you forget what a function's parent or base function looks like. Okay, if you remember the key points of a parent function, a less tedious method to use is called mapping notation, and that's what we're going to be doing in this lesson. So as a recap of the transformations from grade 11, for any function that's written in this form, so y equals a, and then the function k bracket x minus d bracket plus c, this is what the a, k, d, and c mean. Okay, so if the absolute value of a is greater than 1, so this position here in front of the function, what this means is it's a vertical stretch by a factor of a. And now if the absolute value is between 0 and 1, so I like to sometimes call this a fraction, or a decimal, but just remember a fraction may actually be, let's say, 5/2, which is greater than 1. So it wouldn't be that case. It would just be the case where it's like a fraction of 1. Okay, and then that's vertically compressed by a factor of a. Just note, these are the absolute values. So this, I would say, only look at the number. So at the actual number. Well, that's what that means. So ignore the sign. So ignore if it's positive or negative. We're not assessing that. We're just looking at the actual value of a. Okay, now, like number-wise. Now, if a is negative, so this would be negative, which means like less than 0, then our function is reflected across the x-axis. Okay, the next one we're going to touch on is k. So k is going to be, and I always say this, k and d, x lies. So anything attached to this x value is going to be a lie. So I always think of it like, oh, like an ex-girlfriend or an ex-boyfriend. Like, oh, such a liar. Okay, x lies. So anything, the k and the d are going to look one certain way, but they're going to act a different way. So this is what I mean. So if k is greater than 1, then there's the function's horizontally compressed by a factor of 1/k. So you would think that if k is greater than 1, it would be a stretch, but it's opposite. It's actually a compression by the reciprocal. Okay, so we're always looking at the reciprocal of k. And now if k is between 0 and 1, then we have a horizontal stretch. Okay, it's horizontally stretched by a factor, again, of the reciprocal. Okay, so let's just change this to absolute value of k. Okay, again, we're completely ignoring the sign and we're just looking at like the value of just the number. Because when we get down here, if k is less than 0, aka if k is negative, then it's reflected across the y-axis. Okay, those are reciprocal. Okay, on to D. So D again is in this bracket with the X. So the way D looks is not going to be the way D behaves. So as a reminder, there is a negative sign built into this bracket. So we always have to consider that if D is negative, then we're actually dealing with a double negative because of this built-in negative sign. So if D is greater than 0, then our function is horizontally translated d units to the left. Okay, so if d is greater than 0, we're actually going to the right, but what this implies is this is going to look negative. And we want to make this a point here, okay? Because what happens is in this bracket, I'm just going to like extract this bracket. If we had x minus d, this is what happens. If d is greater than 0, let's just take the, for example, positive 5, okay? If we put d minus, and then we put like a positive 5 in here, well, we simplify that to just x minus 5, sorry, x minus positive 5. Okay, so x minus 5. So this is going to look negative, but it's actually moving to the right. And if d is less than 0, so we end up horizontally translating our function d units to the right. But it's actually, this is actually going to go to the left because it looks positive. And I'm going to give you an example of that. If we had d is like negative 6, again, I'm going to extract just the x minus d. If we plugged in negative 6, which is d is less than 0, like negative 6 would move to the left, but in the bracket, it'd be like x minus negative 6, like that. And then it would simplify to x plus 6. So again, this is looking positive, but it's actually negative. Okay, and then the last one over here, C. So if C is greater than 0, then we shift up, so vertically translated or shifted by C units up, and if C is less than 0, we translate C units down. So that's exactly how it looks. Okay, some individuals like to formally put it into this like mapping notation. I do this mapping notation, I do this without this formula, but I think I'm going to start doing it more with the formula for the scope of the videos because it's just more structured. So x comma y is going to map onto 1 over kx plus d, and then ay plus c. And we're going to take a look at that. Okay, example 1, linear functions. So we're going to graph f at x equals x using a table of values. That's the basic linear function, okay? In other words, as a reminder, the f at x notation, this is just the equation y equals x, okay? And then we're going to state the domain and range for it. So let's actually do that now, okay? So we're going to have an x and a y, and then let's choose for the x's -2, -1, 0, 1, 2. Okay, and now if x equals y, -2 equals -2, -1 equals -1, 0, 0, 1, 1, 2, 2. Okay, and now domain and range. Okay, we're going to grab this, we'll put it right at the bottom. So we have enough room. -2, -2. So the graph of y equals x is the base graph for a line without any transformations on it. Okay, in grade 9 and in grade 10, we usually draw a line, not even with like mapping notation, but usually just with like a point, usually the y-intercept, and then applying the slope to that point. Okay, so this is like f at x equals x. Okay, now the domain and range for this one, I'm going to put it underneath. So the domain for all lines is xer, and the range for all lines is yer. Okay, x is an element of the real number system, and y is an element of the real number system. And that's because it goes to the left and to the right forever, and it goes up and down forever. Now for B, for the equation f at x equals 2x minus 3, first what we're going to do is determine the mapping notation. Okay, so if you remember, f at x equals x, and then our new f at x is going to equal 2x minus 3. So this 2 is the a value, and this -3 is our c value. So this 2 means that we're going to have a vertical stretch by a factor of 2. Okay, and you have to write all those words down. And then the C means like vertically translated or shifted 3 units down. Okay, you have to say how many units and where it's going. Okay, so I guess that's number 2 here. The transformations being applied. So we're going to determine the mapping notation. And I like to put this straight into this grid. Okay, for the x value, and put that right here as a reference. Okay, so for the x value, we have to think, do we have a k value? No. So we're going to write x. Now, do we have a d value? Nope. So the x is just going to remain as x. Okay, now for the y value, do we have an a value? Yep, it's 2. So we're going to write 2y. And then we have a c value, it's -3. So 2y minus 3. So this is what we do as a reminder for mapping notation. We take every single value in this x column and we sub it into this equation. Now the x's don't actually change. They remain -2, -1, 0, 1, 2. We can see that there's no transformation on the x. So again, it just remains as x. Now, for the y value, we're going to take the y value and we're going to apply them all. We're going to multiply them all by 2 and then subtract 3. So we're taking these values. So let's do -2 first. So essentially, I'll show you the first couple. We would sub in the -2 to this equation, like 2y minus 3. So 2 times -2 is -4 minus 3. I get -7. Okay, we're going to sub in the next value, -1. 2 times -1 minus 3, I get -5. We're going to sub the next value in, which is 0. 2 times 0 minus 3, I get -3. And eventually you'll be able to do this in your head where you just take the 1 and you sub it in. So 2 minus 3, I get -1. Sub in the 2, 2 times 2 is 4, minus 3 is 1. So this is my mapping notation. These are my transformations. And now these are all of the coordinates for the transform function that I'm going to graph. Okay, so we're going to graph the transform function. So -2, -7, -1, -5. So -2, -7, -1, -5, 0, -3. 1, -1, 2, 1. Okay, so this is now the transform function. Okay, and this is going to be called f at x equals 2x minus 3. Okay, label your graphs, put arrows at the ends of them. Okay, we can see that there's definitely a vertical stretch. What a vertical stretch means in the case of a line is that the slope is steeper. So vertical stretch, steeper slope. Okay, and then what the up-down shift is, so like the shift up or down, what that means is this has to do with like the y-intercept, right? Because usually like in grade 9, we'd be like, oh, we could read this as like, oh, the y-intercept's -3. Well, going down here, well, the y-intercept is -3. And that's just from the shift. Okay, and then as a review, domain of any line is XER. The range of any line is YER. The only time when that changes is when there's restrictions on the actual question itself. For example, if it was like time or like in a word problem. Okay, example 2, quadratic functions. So graph f at x equals x squared. So this is our parent function for the quadratic. Okay, this x squared has no transformations on it, aka like no numbers. The 2 is a number, but it just stands for squared, which is our base graph. Okay, and we're going to do this using a table of values, and then we're going to state the domain and range. So x squared. We're going to use the values -2, -1, 0, 1, 2. And then when we square -2, we get 4. When we square -1, we get 1, 0, 0, 1, 1, 2, 4. Okay, so I'm actually going to graph this and then show you guys what the domain and range is as a review. So 0, 0, 1, 1, 2, 4, and then -3 would be 9. Okay. So as a reminder, f at x equals x squared. Okay. So left and right, which means like these values here, eventually the x values will hit every single value. And so we get the domain is XER, and that is for every single quadratic. Domain's XER unless, of course, it's in a word problem and there's a restriction on the domain. Okay, now for the range, we can start with YER, so Y is an element of the real number system. But here's the thing, we actually like, I want to call it start, but this is technically we start at infinity and we go down and then we go back up to like infinity. But if we take a look at like the lowest number that the parabola hits, we're taking a look at 0 right here, and then it goes all the way up. So y is going to be greater than or equal to 0. Okay, now we're going to use f at x equals -3x plus 5 as the transformed graph. So let's go ahead and write out the transformations and do the mapping notation. Okay, I always do the transformations first. So this negative sign actually means reflection in the x-axis. This 3 means vertical stretch by a factor of 3. And this 5 means like up 5 units. So we can say vertical shift. I'm using the word shift now. Up 5 units. Okay, so let's think about the values that we have. So reflection in the x-axis affects our a value, and so does the vertical stretch. And a shift up and down affects the c value. A and c are generally the transformations that we use on the linear and the quadratic functions. So our mapping notation is going to disregard the k and disregard the d. So our x is going to stay the same. And now ay plus c. So we're going to have -3y plus 5. Okay, because our a value is -3 and our c value is 5. So -3y plus 5. So take all of our x values and we're just going to write them out because the x doesn't change. -2, -1, 0, 1, 2. And we're going to take every single y value and we are going to plug it into this formula, -3y plus 5. So plug in the 4, so negative 12 plus 5. I get negative 7. Okay, negative 3 plus 5, I get 2. 0 plus 5, I get 5. Negative 3 plus 5, I get 2. Negative 12 plus 5, I get negative 7. Okay, so let's go ahead and graph those. Negative 2 comma negative 7. 5, 6, 7. It's going to be around here. Negative 1 comma 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, that's going to be, yeah, that's good. 0, 5. Okay, 1's going to be 2 because this is going to be symmetric. Okay, and then we can label this f at x equals negative 3x squared plus 5. Okay, we can see that we definitely went up 5 for the vertex, and we can see that the a value is negative, so it's opening down. Okay, now domain and range. So the domain on any quadratic is going to be XER. And then the range on the quadratic is going to reference where the vertex is. So the vertex starts at 5 or is at 5. And then because it opens down, we're going to go y is less than or equal to 5. Okay, because the numbers are getting less than 5. Okay, and that's it. Example 3, square root function. So graph f at x equals root x using a table of values, then state the domain and range. So f at x equals root x, that is our square root function. The numbers that we want to use in the table of values have to be able to be square rooted. So let's use 0, 1, 4, 9. Okay, so what's the square root of 0? It's 0. What's the square root of 1? It's 1. What's the square root of 4? It's 2. And what's the square root of 9? It's 3. So if we were to graph this, we would have 0, 0, 1, 1, 4, 2, and then 9, 3. Okay, and it would start at 0, 0, and it would go up to the right with an arrow in the end. Okay, for the domain and range, we do have this like quote unquote starting point, right? We have the origin, which is located at 0, 0, right? It's right here in the table of values. So what we want to do is start with XER such that, and then YER such that. Okay, and we use YER and XER because this is a continuous function. So the x starts at 0, and the x values increase. So x is greater than or equal to 0. The y start at 0, and then the y values increase. So y is greater than or equal to 0. Now let's take a look at the transform function. We'll do this in green. Okay, f at x equals 2 root negative 1/3 bracket x plus 1. So let's list the transformations here. So our a value is vertical stretch by a factor of 2. Okay, we have two transformations here under the root sign, and they're both having to do with our k value. So the negative means reflection in the x-axis. The 1/3, remember we take the reciprocal of k. This is actually a horizontal stretch. And it's a stretch because 1/3, the reciprocal is 3. So by a factor of 3. And then this is the d value plus 1. So that's going to be d, and it's going to be left 1 unit. Right? So that's a horizontal shift. We're treating this root sign as a big fraction. If we had a c value, it would be outside. Sorry, I mean a big bracket. I said fraction. A big bracket. All right, so our mapping notation, we'd have 1 over kx plus d. So 1 over k, the k was originally 1/3, so it's 3. So we're going to go -3, because there's still that reflection, x, left 1 unit, minus 1. And now for the y value, we're going to go ay plus c. So 2y, because our vertical stretch is by a factor of 2, and there's no c value. So we can rewrite our mapping notation, -3x minus 1, and then 2y. Okay, let's sub in. So let's sub in a 0. So 0 minus 1 is going to give us -1. Let's sub in 1. -3 minus 1 is going to give us -4. Sub in 4. -12 minus 1 is going to give us -13. And -27 minus 1 is going to give us -28. Okay, now for the y's, let's double all of the y's. So 0 times 2, 1 times 2, 2 times 2, and then 3 times 2. And let's go ahead and graph. So -1, 0, -4, 2, -13, 4. And then that one's too big to fit on here, which is okay. Sometimes we don't want to zoom too far out on the graph. So we just have our 3 points here. And let's label our graph. So this is f at x equals 2 root -1/3 x plus 1. And our blue graph is f at x equals root x. Okay. So for the domain and range, again, we want to look at our reference point, which is where like the original like starting point would be. So instead of 0, 0, well, 0, 0 is now mapped onto -1, 0. So these are the points that we're going to be referencing. So we start the domain and range both with x is an element of the real number system and y is an element of the real number system. The x starts at -1 and gets smaller, right? Like deeper negative numbers, all the way to -infinity. So x is less than or equal to -1. And now the y values, they start at 0 and increase. So y is greater than or equal to 0. Example 4, absolute value function. So graph f at x equals absolute value of x using a table of values and state the domain and range. So the absolute value x function is going to look like a v, okay? So the x, what we're going to use for the x is -2, -1, 0, 1, and 2. And if you're not too familiar with the absolute value function, absolute value means all the time it means take the positive. Okay, so the absolute value of -2 is just 2. The absolute value of -1 is just 1. Absolute value of 0, 0, 1, 1, 2, 2. Right? So the ones that we really had to change here are just the negative ones, like the negative coordinates. So what that looks like when we graph it is 0, 0, 1, 1, 2, 2, -2, 2, 3, 3, -3, 3, 4, 4, -4, 4, and so on. So this is very similar to y equals x. In fact, this side is y equals x, but instead of going down here, what the absolute value function does is it reflects anything in the lower quadrant up so that it becomes a positive. Okay, now let's take a look at this function here and let's list the transformations and determine the mapping notation. So this -3 is actually two different transformations. The first one is reflected by a factor, reflected in the x-axis. The 3 is a vertical stretch by a factor of 3. Okay, and both of these are the a value. Okay, 1/2 is going to be, that's the k value. And remember, this one's backwards, it's the reciprocal. So it looks like 1/2. So this is actually a horizontal stretch by a factor of 2. Okay, and then the -3 means right 3 units. And that's going to be our d value. You can say like horizontally shift, but ensure that you have the right 3 units in there. So when we're thinking about mapping, okay, so here's our mapping. XY maps onto, so let's go 1 over kx. So our k value is 1/2. So we take the reciprocal, 1 over k. So 2x, and then we have plus d. So here's the thing. It looks like a -3, but we're going to the right. So we're going to go plus 3. Our actual d value is 3. Okay, and then ay plus c. So we don't have a c value. It would be over here. The a value is -3. So we go -3y. So from the original, all of the x's, we are going to multiply by 2 and then add 3. So -2 times 2 is -4, plus 3 is -1. -1 times 2 is -2, plus 3 is 1. 2 times 0 is 0, plus 3 is 3. 2 times 1 is 2, plus 3 is 5. 2 times 2 is 4, plus 3 is 7. So those are our new x coordinates. Now, all of the y coordinates, we are going to just multiply by -3. So 2 times -3 is -6. 1 times -3 is -3. 0 remains at 0. 1 times -3 is -3. 2 times -3 is -6. So let's go ahead and plot -1, -6, 1, -3, 3, 0, 5, -3, and 7, -6. And we can see that this is definitely in the shape of a V. We have symmetry here. And we can label this. F at x equals -3, 1/2 x minus 3. And we can label this as the original f at x equals absolute value x. So domain for the absolute value function is xer, because it extends to the left and to the right forever. Okay, and then the range, well, we can kind of compare it to the quadratic function where we start, and I use that loosely, start at 0, 0. Okay, so the lowest point on the absolute value function is 0, and then the absolute value function increases. So y is an element of the real number system such that y is greater than or equal to 0. Okay, and for the transform function here, the domain is going to be the same, XER. Now, I'm going to set up the range. Y is an element of the real number system. So there is no shift up or down. So again, we're referencing the 0 on the y-axis. But this time we're going down. So y is less than or equal to 0. Example 5, cubic function. So graph f at x equals x cubed using a table of values, then state the domain and range. Okay, so x cubed may be a new function for advanced functions here. So all we have to do is I'm going to choose to do -2, -1, 0, 1, 2. Okay, and all we have to do is take each one of these values and plug it into where the x is. So all we're going to do is cube it. So -2 cubed is -8, -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. So that's going to be our table of values that we use for the parent function, f at x equals x cubed. Okay, and we can go ahead and graph this. So 0, 0, 1, 1, -1, and then 2 and 8. -2 and -8. Oops. Okay. So this is what this graph looks like. Okay, if I were to draw this just freehand, I would draw it like that. Just as an idea. Okay. Now the domain and range for this function. Okay. This function goes to the left and to the right forever, so XER, and it goes up and down forever, so YER. Okay, X and Y are both elements of the real number system. It goes this way forever, and it goes this way forever. It goes up and down. Okay. Now, for the equation, f at x equals -3 times 2x minus 2 cubed plus 5. We're going to go ahead and determine the mapping notation. I'm going to first state the transformations of this function. So, the -3, this is the a value. These are two different transformations. So I have reflection in the x-axis. Okay, again for the a value, I have vertical stretch by a factor of 3. Okay, the k value is 2, so we're thinking 1 over 2. So we're thinking horizontal compression by a factor of 1 over 2. This is our d value, so we're going to go right 2 units. And then our c value is going to be up 5 units. So when we consider the a, the k, the d, and the c when we're doing our mapping notation, so 1 over k is going to be 1 over 2 x plus d, so it's right 2, so it's plus 2. And then for the ay plus c, we're going to have -3y plus 5. So I'm going to go ahead and put in the 1/2 x plus 2, so the mapping here, -3y plus 5. And let's sub all of our x's into this equation. So what's a half of -2? Well, it's -1. Plus 2 is 1. Okay, a half of -1 is -1/2. and then plus 2 is like 1.5. So if you can put 1.5, you can put 3 over 2. Doesn't matter. Okay, 0, so 0 plus 2 is 2. 1, so 1/2 plus 2 is 2.5. And then 2 times 1/2 is 1 plus 2 is 3. So these are our new x values. Now, our new y values, we're going to sub in all of these y's to here. -3y plus 5. So -3 times -8 is 24 plus 5. We're going to get 29. -3 times -1 is 3 plus 5 is 8. 0 plus 5 is 5. 1 times -3, so -3 plus 5 is 2. And -24 plus 5 is -19. So let's go ahead and graph this. Okay, 1 comma 29 is going to be here. 1.5 comma 8. 2 comma 5. 2.5 comma 2. 3 comma -19. So we can see that this is still flattens out in the middle, but it gets really stretched there. Okay, so this is our f at x equals -3 to x minus 2 cubed plus 5. Okay, the last thing, domain and range for our transform function. Okay, so x is an element of the real number system, y is an element of the real number system. These don't change. Again, unless this is a word problem and there's restrictions on the domain or range, but both of them should be XER. Example 6, reciprocal function. So graph f at x equals 1 over x using a table of values, and then states the domain and range. So f at x equals 1 over x is a very unique function. Okay, so the only two values that I use are -1 and 1. So if we sub in -1, we'd have 1 over -1, which again would yield -1. And if we subbed in 1, we'd get 1 over 1, which would yield 1. Now the extension is that there is a horizontal asymptote okay, and there's a vertical asymptote. So horizontal asymptotes go this way. We draw them with a dotted line, and they are in the form y equals, and then a number. So in this case, y equals 0. And the vertical asymptote is in the form x equals 0. Okay, and vertical asymptotes are up and down, x equals 0. Okay, so what we see with the first, there you go, what we see with the original 1 over x is we see this vertical asymptote, we see this horizontal asymptote, and we have to label them. So this is y equals 0, and that's a horizontal line. And then the vertical line is x equals 0. The 2 points that we plot, 1, 1, and -1, -1, all we have to really do is find out which, and I call them quadrants, which quadrants the 2 points are in, because that will tell us that our graph is graphed here and our graph is graphed here. Okay, this is one function, this is one graph, even though it's discontinuous. So that means that we can draw half of it, pick up our pencil, and then we'd have to draw the other half separately. This is still one graph. Okay, so when we're talking about the domain and range, our x and y are going to hit every single number except for the asymptotes. So, for example, if we're looking at the x values here, we're going to hit every number except for 0. Okay, and when we're looking at the y values, we're going to hit every number except for 0. And that of course is from the original. So x does not equal 0, y does not equal 0. And you can put a note for yourself, x does not equal the vertical asymptote, y does not equal the horizontal asymptote, because these numbers are going to be straightforwardly right there. Okay, now let's take a look at the transformations. So for the equation, f at x equals 1 over x minus 3 plus 5. So let's first say the transformations, then we'll do the mapping. Okay, so around the x, this is going to be the d value. So for our d value, we have right 3 units. And for our c value, we have up 5 units. So I put this on our page. We have no stretches or compressions, so we're going to get rid of the 1 over k and the a. Like the values for there wouldn't be 0, they'd be 1. Like we would have the same stretch value as the original or the same compression value as the original, which is nothing. It's just the original. Okay, that's how it references. Now, for the d value, we're going right 3 units, so we're going to go x plus 3. And for the y value, we're going up 5, so y plus 5. So let's take all of those values for x and y, those two values, and we're going to go x plus 3, y plus 5. So negative 1 plus 3 is 2, 1 plus 3 is 4. Negative 1 plus 5 is 4. 1 plus 5 is 6. And we do the same thing for the horizontal asymptote and the vertical asymptotes. So check this out. Because it says y equals, we're going to put this into the y equation. So y equals, and then it was originally 0, so 0 plus 5 is 5. And the vertical asymptote is x equals, and the original was 0, so 0 plus 3 is 3. So when we go ahead and graph this, we're going to graph a horizontal asymptote at 5, a vertical asymptote at 3, and from creating these two lines, we'll mark off x equals 3, y equals 5. What we're going to do is we're going to plot those 2 points and see what like quadrants it lies in, quote unquote quadrants. Okay. 2, 4. So 2, 4 would be here, and 4, 6 would be here. So all we do is we graph our 1 over x function so that it approaches both the vertical and the horizontal asymptote. And we can go ahead and label it. F at x equals 1 over x minus 3 plus 5. And I forgot to graph this one. F at x equals 1 over x. Okay. We can set up the domain and the range the same way. XER such that x does not equal a number. And we can set up the range the same way, like YER such that y does not equal a number. And the domain can't equal the vertical asymptote, so the domain can't equal 3. The range can't equal the horizontal asymptote, so the range cannot equal 5.